Hello everybody, and welcome to part 2 of our Carver MXR 2000 stereo receiver video. In this part we're going to focus on the magnetic field power supply. Now, one of the big buzzwords that you hear with Carver audio gear is the magnetic field amplifier. And at the heart of the amplifier there's really two parts that they use. Part of it has to do with the power supply itself, and the other part of it has to do with something that they do in the output section of the amplifier. The amplifier portion of that we're going to handle on the next video. This video is going to focus strictly on the power supply itself. So the first part of this, I'm going to talk about some things that might be some review for some of you, so feel free to skip ahead because we're going to talk a little bit about what a triac is and a little bit about transformers and how they work, so that kind of help us to understand a little more of what's going on with the Carver quote-unquote magnetic field amplifier. Okay, the first thing we need to know is, before we even get into any of this, the word in itself, or the phrase magnetic field amplifier or magnetic field power supply, is a little bit of a marketing thing, at least in my opinion. And the reason I say that is that, of course, any power supply that uses a transformer is going to incorporate a magnetic field, because, of course, whenever we take an inductor and we wind it around a magnetic core like steel or iron or something, some ferrous metal, it will create a magnetic field. And even in air, the center of a inductor, of a coil, will have a magnetic field, even though the field may not be as strong as if you have something like ferrous in it. It still involves a magnetic field. No transformer can work without a magnetic field. So really, saying it's a magnetic field power supply is just basically, to me, saying that it's a power supply that uses a transformer. So let's ignore the terminology that was used by Carver Marketing for a minute, and let's focus a little more on what they did different in their power supply that you don't see on the typical power supply. Now, on our channel here, we've done an awful lot of service on different makes and models of stereos, and they've all used a traditional linear power supply with a great big transformer, a bridge rectifier, and capacitors. And so we're all very familiar with that. If you're not familiar with how a linear power supply works, if you're new to this hobby or something, I suggest you go back through my videos. And a few videos back I did a little video on linear power supplies and how they work. So go back and watch that. For the rest of you, let's just kind of talk about what's going on. So above here, what we see is this is a conventional power supply, and this is an oversimplified drawing, just a very simple drawing of a linear power supply. So this first thing here we see is the transformer, and the transformer consists of two inductive coils of wire, the primary and the secondary. The primary is the input, think of where our AC mains is going to come into, and the secondary is going to be the output. In the middle of here is a magnetic material, which would be a steel or iron core or ferrite. There's different materials that are used, or in some instances even air. And then we have our secondary, and as we know from our linear power supply video, at line frequency at 50 or 60 hertz, the input number of turns, if you count the number of turns versus the number of turns on the output secondary, that will give us also the ratio of the voltage. So if you have 1 turn here and 10 turns here, if I put 1 volt here, I'll get 10 volts here, and vice versa. So you can use it to step up or step down. But of course, the law of conservation of energy, we can't create or destroy energy. We can only change it in different forms. So if we increase our voltage on this side, it will have less available current because the overall wattage, with the exception of the losses in the transformer and so forth, the wattage has to be equal on both sides. So that's how a transformer works. And I know that there can be a little bit of confusion with the Carver equipment because a lot of that terminology can lead you to believe that something more than that is actually going on. But in fact, a Carver amplifier with a magnetic field power supply is still using a transformer, and it still consists of a primary and a secondary and a core, a magnetic core. So it's just the same as any other transformer, albeit it's a bit smaller. And we'll get into that later on in the video. The other part to a linear power supply is a rectifier. A rectifier just takes the alternating current that is required by the transformer for it to function and converts it to a direct current. Now, a lot of people that are new to electronics kind of get a little confused about DC. DC doesn't necessarily mean that it is a constant voltage. It just means that the voltage never changes polarity. So if this is the positive and this is the negative, it will always stay positive and negative, even if the positive and negative here are alternating back and forth. So this may be a pulsed DC. In other words, it may be a DC that goes from 0 to a certain level and then back to 0 again and back to a certain level. Or it could be a smooth DC, depending on what we do to the power supply. So all this does is it ensures that the voltage can only flow in one direction, or the current can only flow in one direction, not the other. Now, in order to get rid of those bumps, to get rid of that wavering DC pulse, we use a capacitor. And the capacitor, of course, acts as a filter. It will charge up to the level of the peak of this, and then it'll stay there. And as it's discharging, this is refilling it every time it pulses. So in its simplest form, a linear power supply is just these three parts here. It's your transformer, your rectifier, and this doesn't matter if it's a half wave, which is what this is, or a full wave, or a bridge rectifier. You're still taking the AC and converting it to DC. And then the third part is this capacitor. 3 parts. And really, they're only doing one extra part when we talk about the magnetic field power supply. So if we look down below here, it's the same thing. Ignore these 3 taps because this is a tapped power supply with different voltages at each tap. And we can learn again about that from our linear power supply video. But really what we're concerned with is this little component here. And this component here, this is a schematic symbol, and it's not 100% correct. Let me add a part to it, if I can find a pen. There we go. This device is called a triac. And a triac, think of it as a switch. If I apply a small voltage or a small signal to this little wire here, this is called the gate, okay? And then these are your main terminals. There's main terminal 1 and main terminal 2, okay? And essentially, if I turn this on, it allows the current to flow in both directions. Notice the arrows are turning, facing both directions. And notice it looks similar. If you look at just half of it, if you only look at a half, it looks very similar to these diodes. And it does have some similarities to a diode. As a matter of fact, when we have this extra element here, if we only look at this one part, this is what we could refer to as an SCR. And what a triac is 2 SCRs electrically connected inside one case, and they're wired reverse polarity to one another. So if you notice, one of them is facing one way and the other is facing the other way. And this one also has a gate on it, but we just don't show it because the gates are internally tied together. So how does an SCR work? This is extremely important because this doesn't work just like a switch. If we put a switch in here, if I turn the switch on, the signal will just continually flow in both directions, and it will, whatever is here will appear here. It's no different, it's not changed. And if I flip the switch off, it will turn off immediately. That is not exactly how one of these works. And in order to understand how one of these works, let's do a little demonstration. To make it simple, we're only going to look at an SCR, because really an SCR works the same way as a triac, but it only works in one direction instead of both directions. So let's look at it. All right, right here we have an SCR, and you can see this is just a small one, and all SCRs are very similar, so the only difference between this little tiny one and the great big ones is the bigger ones can handle higher current and higher voltages and so forth. So this is just a low power SCR. But SCRs all work the same way. They all have the same three elements: anode, cathode, and gate. And if we look at this little symbol here that I drew, if we look at the top looking down, okay, the anode is on this end, the cathode is on this end, and the gate is in the middle. So it would be just like this. Okay. And if we look at the schematic symbol, the anode, the cathode, and the gate. So it looks very similar. If you took the gate out, it looks just like a normal diode. Now, an SCR has some certain properties to it. As long as current is flowing in the SCR, it will function as a diode. So what's that mean? Well, let's do a little experiment. I've taken that SCR and I have essentially attached, and I'm looking around the camera here, so my drawing is going to be pretty bad. And I've taken an LED and I've put it in series with this. So we're going to put our voltage just like this, and we're going to, this is how I have this connected. So if we look here, here's your SCR, here's your anode, your gate, and your cathode. And if you notice right now, let's take the lights all away for a minute. If you notice, the LED is not lit. But if I take the gate wire and I just temporarily touch it to the, and by the way, you have to watch doing this because you can damage the component if you don't have a current limited power supply or you have too much voltage. Okay, so I'm making this very simple. Normally there would be some other like resistors and so forth in here, but this is just to show the concept. So if I take this gate and I touch it to my anode, the light lights. See that? It's lit. But if I take the wire away, it stays lit. It won't turn off. And the only way I can get it to turn off is to actually remove the voltage altogether. Then if I put it back on, it's reset. Now it will not start again until I trigger it with the gate. So let's touch this again. Now if I touch the other side, it won't do anything. But if I touch this side, it lights. So we learn a couple things from this little experiment. Number one, an SCR will not conduct between the anode and the cathode unless you put some sort of a trigger voltage onto the gate. And the second thing we learned is once we trigger the gate, we can remove the voltage from the gate and the SCR will continue to conduct until that voltage goes away. So you actually have to remove the voltage for it to work. Now, why is that so important? Well, we're going to see when we deal with AC why that's important and how it affects an AC waveform. Now, what is a triac? A triac would be like taking two of these and putting them back to back. So let's put this one in backwards, like this, if I can see around the camera. And let me add another LED. Hold on a second. Okay, we now have two of these SCRs wired parallel back to back. So if we look, we have the anode and the cathode in the original direction on the first one, but on the second one we have it facing this way, and they're connected together, so you can see them right down there. Now, if we do our same experiment the same way we just did, we take this and we touch it up on this side where the anode is, the same lights. Okay, do you see? So this light is lit, this light is not. And if I extinguish this, I can even touch it on the opposite one, and nothing happens. So it's just in this one direction, still works like a normal SCR. However, if I flip-flop these two wires around and I change my polarity, if I do my little experiment, nothing lights up. However, if I touch this on the opposite side now this one lights up and this one does not. So what we have is something that can work both polarities. And that's what we're showing. And that's what the whole purpose of a TRIAC is, so that it can conduct in either direction. And when you trigger it, it doesn't matter which polarity your source is connected in, positive or negative. It will always turn on in that direction if you trigger the gate. So that's what a TRIAC is, and that's how it works. So now let's go back down and look at our little symbol again. Now returning to this, we can tell that we now have established that by gating this on, this can conduct in either direction, and it doesn't matter which half cycle you're on, this thing can conduct in either direction. Now, here's the problem. The only way this can turn back off is two things have to occur. Number one, I have to remove my voltage from my gate. That's number one. Number two, this has to return to zero. This is called your zero crossing. When this cycle goes and it goes down to 0 volts, and then the polarities flip from positive to negative, negative to positive. Okay, at that point, you have to be at that point before this will shut off. And then, if there is no voltage present at this gate here, it will stay off. If the voltage is still on, even though this one turns off, this one will turn on, and vice versa. So as long as there's voltage here, this will come on here. The other thing is the timing of when I turn this on. We don't know if when I was putting that little wire on there on the trigger, I don't know at what point in this cycle this is moving. So wherever it is at the time that I touch this, that's when it'll start. So for instance, if we're all the way up here at this part and I touch this gate, this will be turned on, and you will have voltage or current flowing through this transformer all the way from here down to here for this entire time. If I touch the wire when we're at this part of the cycle, I'll have this much of it. It will stay on from here until here. Now, if I have a way of knowing where this is in this waveform when I turn it on, I can control number one, how high of a peak is turned on. So if I turn it on, so if this peak is 170 volts, which would be V peak of your 120 volt AC RMS line of your mains voltage in USA. If I have 170 volts up here, but I turn it on here, down here we might only be 100 volts. So if I only turn it on here, and then I let it shut off, and then I trigger it again when it gets up to 100 volts, it'll still go all the way up here. I have to leave this and then wait till it gets down to 100 down here. And right here, this will be turned on. I will only put out 100 volts. If I turn it on right at the peak and right at the peak, then all of this is filled in, right? All of this is turn on time. And for this period and for this period, I will have the full 170 volts plus whatever, the remaining as it goes down. So that's why when you look at those waveforms that we looked at, like in the first video, you saw that funny looking, if you remember, it didn't look sinusoidal. It kind of came over like this, then it went straight up, then it kind of hooked around like that, then it went straight over, then it kind of went straight down, and it hooked back up like that. That's roughly what it was doing. Okay? And this portion of it, and this portion of it, was not there. And that's why. Now, the Carver magnetic field power supply monitors this waveform, and it can tell this gate when to turn on. It can't tell it when to turn off. That's the trick. This cannot shut this off. It has to wait for it to extinguish itself. This is called self-extinction. There's two ways to turn this off. There's self-extinction and forced extinction. Forced extinction would be to put an equal and opposite polarized voltage into this to force it to shut off before you get to the zero crossing. We're not going to talk about that, though. We don't use that in this circuit. This is a self-extinguishing circuit, so that means it has to rely on the waveform to play itself out and get back to the zero crossing here or get back to the zero crossing here before this can shut off. But what we can do is only allow a portion of that signal to get out to here. And that is what they're doing. Now you might ask, why are we doing this? Okay, that was the $64 million question. Why do we want to do that? Well, there are several reasons, and we'll get into them here in a minute. Okay, here we have two transformers. Okay, this one is physically larger than this one, as we can see. And these are different windings. Just ignore that. But let's pretend that this transformer has the same amount of turns on the primary and secondary as this transformer. So they both have the same turns ratio. So let's say this one was designed to have 120 volts in and 12 volts out, and this one also was designed to have 120 volts in and 12 volts out. If I do not connect any load to the output of these, and I put my 120 volts in and measure them both, they would both work the same. I would get the same voltage out. There would be no difference between the two of them. So why would I have to have this great big thing if this thing will put out the same voltage? Well, really it's all about the wattage, or the overall power that this transformer can deliver. And of course, wattage is a product of the voltage and the current. Okay, so this transformer has a larger coil in it, and it has a lot larger core in it, magnetic core. In other words, this magnetic core has the capacity to store a much larger magnetic field than this one does. So this creates a large magnetic field. This creates a small magnetic field. And the problem with that is, as I apply a load to my output of my transformer, the more load I provide on this, the more that magnetic field is going to, the quicker that magnetic field is going to collapse, because it's not strong enough to maintain the field that this output coil needs to produce that kind of current at that voltage. So what happens is this transformer will saturate, is what they say. So when it saturates, that means there's no longer enough magnetic field to support the voltage and current that the secondary coil is trying to provide. And as you could tell, this being a much smaller core is going to have a much smaller magnetic field and is going to saturate much faster than this one. Now that's how conventional transformers function. However, these transformers of this size and not a whole lot bigger can be used to actually produce voltage and current the same level as this big one. Now how do they do it? Well, in a modern power supply, and let's get one out. Okay, so right here we have a modern power supply. Now let's take a look at this transformer for a second. It is capable of delivering, if you can see that, I don't know if I can see that in the light properly, it can deliver 3 amps maximum. That's all that this can deliver before this core can no longer, and the coils and the wire and everything can no longer supply the voltage and current that's being drawn. Okay, so 12 volts at 3 amps. If you compare that to this power supply, it has a transformer as well. It has a bridge rectifier. There's a lot of similar components. It has the capacitor. But if you look at the transformer, it's tiny. So this probably is way less than 3 amps, wouldn't you think? But when we look at the supply, it can put out 5 amps at 12 volts. So how in the world does this tiny little transformer deliver the same amount of current or more current than this great big transformer? Well, the secret to it is this is called a switch mode power supply, or a switching power supply. And it actually runs at high frequencies. It's no longer running at 60 hertz. And by providing very quick, sharp pulses of voltage, the transformer, we're able to kind of trick that core of this transformer that it's never on long enough for the core to saturate. So just about the time the core is ready to collapse and that magnetic field is ready to saturate, it shuts off, and then it's given another big pulse again to charge it back up. When we look at this, that's what they're doing here. Now, the only thing is, this is a much more antiquated way of doing it, because what we're doing is we're not really turning on pulses very quickly. In other words, this is still running at mains frequency, 50 or 60 cycles per second, or 50 or 60 hertz. But what we are doing is something similar by only turning on the transformer, or the power to the transformer, long enough for it to charge up, and then just before it collapses the magnetic field, we're going to pulse it on again. And for that off time, it's not sitting there idling with the magnetic field changing, because we are changing the voltage. Now, one of the side effects of that is, instead of the transformer building up voltage and building up its magnetic field slowly from 0 to peak and then slowly decaying back down to 0, if I turn this on right here, all at once, I'm actually putting 170 volts right across the coil of this transformer, and of course for that split second it is going to draw really high current very slowly, or very quickly though, for a short duration. So whenever you hear these Carver amplifiers make that really grunt sound, that's because of how abruptly the power is being switched on to the input of the transformer. That's what that grunting is. And of course, the higher the power you're drawing, the longer the period of time that this is staying on, and the quieter the transformer gets. So if you notice, like in video number 1, as I turned the volume up on the amplifier and more demand was being drawn from this transformer, it actually started to get quieter, not louder. And when I turned it down, it actually got louder again, because again, we were making these little turn-on durations shorter and shorter. So that's what they're doing. Now, how do they do that? Well, let's take a quick look. Okay, remember earlier when I said I don't know in that waveform, once again, I don't know what part of this cycle, when I hit the power switch on this amplifier, I don't know where in this cycle I am, because I can't see it when I push the power button to turn the receiver on. So at any given time, this can be anywhere when I hit that button. That's why if you ever notice on a Carver amp, if you turn it on, sometimes when you turn it on, it makes a really loud buzz and a really loud grunt. Other times when you turn it on, it makes a quiet grunt and starts up. Different every time. That's why. However, once you get through one complete cycle, we have a circuit here that's going to monitor that. And the whole purpose of this is to monitor the current. If you notice, it's kind of tied into here, and it is monitoring the output of these. If the voltage changes or the current changes, this circuit is actually designed to change the cycle, the turn-on cycle of that trigger, okay, of this gate, to make it turn on sooner or later, depending on how much demand there is from the power supply. That's what this whole circuitry up here does. And everything's all monitored by that. You can see here's your little relay though. This relay is going to be controlled by me pushing the on-off switch. So the very first turn on is going to be pretty much where it's going to be. And then once this thing goes through a cycle, all of this circuit starts reacting and it'll regulate. The other thing is, when I first turn this on, there's going to be a surge current as the capacitors charge up for the first time. Now the biggest capacitors are on the amplifier board. These are low voltage, but the actual main high current power supply is on the amplifier board, and it's not on this power supply board. So that's essentially what's happening. This whole circuit is monitoring that zero crossing. It's monitoring the amount of current being drawn by this transformer here. Remember, we said this transformer is a constant on. It's a small transformer, and it's only providing the low voltages up through these regulators for the turn-on circuit, for the tuner, for different things like that. Whereas this is the magnetic field, quote-unquote, transformer that provides the high current power for the amplifier. And you notice it's in that little box. They put it in that little aluminum cover, as we saw earlier, which permits, which kind of helps to quiet it down, and it also provides shielding. Remember, this is a pulsing transformer, so it no longer has a sine wave on it. There's going to be harmonics and all kinds of noise generated, and if you don't shield this transformer, it could technically induce noise into your tuner, into your preamp, into your phono stage. So this is all shielded inside that aluminum cover. So that's what's going on here. So now let's take a look at a few other things. We'll actually put the amp up on the bench, and we'll kind of look at some of these things. Okay, looking at the innards of this power supply, you can see that right here, this in fact is the triac, and it's the same one if you go back to the M400 Cube video or even the Silver 9T video. It's very similar to those. It's just a chassis mount that they soldered in upside down onto the board, and then the bottom part that would normally be mounted to a chassis, they mount to this little heatsink. And then here's that little power supply that we were talking about. This is the little transformer for the regulated power supply that we use for the turn-on circuit and the low voltage power and so forth. These are the filters and the regulators and all that, and the little power on relay that's controlled by the power on switch. So this is basically your low voltage power board and your turn-on circuit all here. And if we lift this up, just like on the first video we saw this, you take this little cover off, and there's your magnetic field transformer. And if you look, go back through some of the old videos of like the Sansui 9090 or the Pioneer SX1250, both of those have about half the output power that this amp is supposed to be rated at. They're like 100 and anywhere from 120 to 150 watts per channel. This one's 200 watts per channel. And if you look how massive the transformers were in those receivers, and you compare it to how tiny this one is, that's one of the advantages of the magnetic field power supply that Carver designed. Again, it's, similar techniques have been used in other things, but this was really the first time that something like this was implemented for audio like this. And this is an evolution of the Carver equipment, in that you're going to find out as we do the more parts to this video, you're going to find out that this is a more refined version of all of his things from the original ones that came out on the earlier models of equipment. Okay, I hope I have everything in the shot here. So what we're looking at right now, the receiver is turned on at the moment, and if you look, this is what's left of our incoming 120 volt AC line mains voltage coming in. So this is the output of that triac, and conversely it is also the input of the power transformer. Channel 2 is connected across the dummy load of the speaker terminals. So we're just looking at the output of the amplifier, and we're going to drive a signal into it. And as you can see right here, our 70 volt power supply is sitting just under 70 volts at 69.74 volts. And I'm on the negative, by the way. I'm looking at the negative rail. It doesn't matter. The positive rail would be positive 69 volts or whatever. Now watch what happens as I increase the volume. Remember, if we increase the volume on the amplifier has to deliver that power to the dummy load. So as the amplifier calls for more energy, this is going to have to work harder to keep up with your DC power supply here. And if this adjusts properly, then this should stay at that 70 volt range without dropping. Now, if this doesn't change and we increase the volume and of course increase the power draw of the amplifier, this would drop, because with Ohm's law something has to give somewhere. If you don't have enough current available, then your voltage has to drop if your resistance stays the same. So everything always has to balance out because of Ohm's law. So let's turn this up and see what it looks like. So you can see right now I'm just beginning to deliver some power to the dummy load. And you can see our voltage is not changing, but this has gotten a little bit larger of a waveform. And watch, as we go up in power, we'll take it all the way up to clipping. And right about there we're clipping. That's about 200 watts of power right now. And if you notice, there is a slight bit of drop on our power supply, and that's because of my incoming line. I have everything connected to a isolation transformer, and because this is a 2-channel 200 watt per channel amplifier, that 400 watts is coming close to the limit of what my isolation transformer can deliver. So that little bit of drop, we're actually getting some drop on our amplitude here. But if you notice, if I just go up to like 10 or 15 watts, if anything, this power supply will go up a little bit. See? Now it's 70 volts. So it actually is keeping up with the demand of the amplifier. And that's really the whole theory behind the magnetic field amplifier, or power supply. Now the amplifier is a different story, and that's going to be a different part of our video series. We're just going to talk about the power supply portion right now. And I just wanted to show the interaction between the triac and that whole feedback circuit of the triac versus how much energy the amplifier is drawing at any given time versus the actual power supply. Now, on a standard linear power supply amplifier, what you would see is this would be a perfect sine wave. And you can see the higher I turn the power, the more sinusoidal this begins to look. You see how this is all turning into a sine wave with just a little bit of clip out there? And with a linear traditional power supply, this would be a normal sine wave. It wouldn't be broken up like this. And it would have to be a very high energy power supply to deliver that kind of power and maintain voltage. Because remember, if the transformer doesn't have enough magnetic material in it, or the iron or steel core, or whatever you want to call it, and the windings aren't heavy enough and so forth, as you draw excessive current, that linear transformer would start to, number one, it would get hot, and number two, it would start to drop in voltage as you're increasing the current. And the theory behind this is a smaller transformer than would normally be able to deliver that kind of current. But since there is an off time on that, it actually acts like little pulses and allows a smaller transformer to deliver greater amounts of current and still maintain its set voltage. And that's really the whole theory behind this magnetic field transformer. It's not really the same as a switch mode power supply, but it's related to it. Of course, this thing runs on mains frequency. So in America it's 60 hertz, Europe it would be 50 hertz, but nevertheless it is varying the off time is what it's doing. So I hope that makes a little more sense how this thing works. And all this circuitry down here, as I bang my camera into everything, all this circuitry down here, its whole purpose in life is to monitor that current and voltage and change the drive of this triac gate as the demand on the power supply increases or decreases. And that's the whole point. That's why these amplifiers run very cool. Now, I don't want to get into the output transistors and things like that. That'll be the next part of the video. But this video was just for the purpose of kind of showing you how this magnetic field power supply functions.